Good evening, everyone. Welcome to UACNJ. I'm Paul Fisher. I'm the current UACNJ president. And before we get started tonight, I would like to take a moment on this solemn anniversary to remember all the people, victims, families, and friends, the survivors, first responders, and everyone else throughout the world affected by the horrible events 20 years ago. Please join us in a moment of silence. Thank you, everybody. And now we will continue with our regularly scheduled program.
All right. Thank you, everyone. Thank you for coming and joining us here at United Astronomy Clubs of New Jersey. Couple things to note, as I'm sure our online audience has heard from Matt, who has been doing our intro. We are doing this live on location at our Jenny Jump facility in Hope, New Jersey. So we do have a live audience on hand, and for the audience's information, we also stream this live to our YouTube channel. So if you ever can't make it, or you're feeling under the weather and looking for something to do on Saturday, but still want to stay home, you can check us out on our YouTube. We do stream all of these live Saturdays, but we also keep all of our past presentations that we've been streaming live on there too. So if you see a program on our list that you would have found interesting, you can always go back and actually look at what those programs were. So, I am monitoring chat via my handy dandy mobile device. It's really become the MacGyver, do-all tool, the Swiss Army knife of today's world. But I just want to go over a couple things. Please check out our website, uacnj.org. That is where you can find all the information about us as a organization. You can find information on our member clubs, because we are a consortium of various astronomy clubs throughout the New Jersey, and a couple in actually New York and one in PA, astronomy clubs in the area. So if you want to find out information on that, like I said, check out our website. We also have a presence online through Facebook, Instagram, Twitter. We now have opened up a Discord server for any of the younger generation who like to get on Discord. I'm sure you'll find us there. We are a nonprofit organization. So everything, all your guys' help, the fact that you come out here every night, the fact that you check us out on our YouTube does help to showing that we are wanted, and we love the support. All your donations that you have done have helped keep our lights on and help keep us going throughout this pandemic. So with that, for our live audience here, a couple safety things. If you need to use the bathroom, I have the porta potty right over to my right, your left. After the presentation, after the Q&A, I will be manning the gift shop desk over to my left, your right, and like I said, all the proceeds go to help supporting us as a club, keeping our lights on, keeping us offering the free public program. Because when you go to our website, you might need to sign up for a reservation to be able to attend a public night. It is still completely free to do so. So we do not charge anything for you guys to come out. It's just with the pandemic, we have had to limit crowd size and whatnot just for safety reasons. So after the talk, we do have multiple, as people have noticed, sheds. They have the roll-off roofs. Each one of those is actually an observatory and contains a telescope. Now, with, again, the pandemic, the sanitation required to look for, we believe, would destroy our eyepieces if we were to do that between every person. So for all of our club scopes, so UAC and J scopes, we do have cameras set up where the eyepieces would normally be, and we do have the projector screen set up so that you would be able to still see what it would look like through the telescopes. And when you please go to leave, use your headlights. We don't like getting run over, and we like seeing where people are. Conversely, if you do need light to walk around, please keep it pointed towards the ground, just because we don't like blinding people. You can move your flashlight, can't really move a headlight, so we are understanding that way. And with that, tonight's presentation is All Our Energy Comes from the Stars with Dr. David Buckley. Dr. Buckley has been teaching astronomy and physics at East Stroudsburg University of Pennsylvania for 3 decades. He studied physics at Rutgers University. He got his MS in astronomy at Penn State. No, I alternate scrolled and I'm like, oh no, lost my place. Where's the cursor? And his MS in physics and a PhD in astronomy at University of Massachusetts, Amherst. If I got that abbreviation correct. His dissertation research was on planetary nebula, and he is currently trying to develop a student research program in photometry?
Yeah, photometry.
Photometry. I'm learning how to pronounce all the new words. And he would welcome any tips and suggestions from experienced amateurs. He most recently was an educational consultant at Black Rock Castle Observatory in Cork, Ireland in the summer of 2019. And with that, here's Dr. Buckley.
Thank you so much for the introduction. Thanks, everybody. I usually get a better view of my audience, but we've just gotten back to in-person classes, so I don't really recognize my students because it's all from the nose up. But that's okay. I'd rather be in person, nose up, than not in person. I was very tired of teaching to little black rectangles on the screen from last year. But at any rate, welcome, and it's a pleasure to be here. I actually wish I knew about this organization years ago because I was the founding member of the Junior Astronomers Club in 1970. And we had a total of 3 members. And we lasted for about 2.5 years until my friend, who was the other member of the club, moved to Colorado. But it was a good beginning, and I ended up turning my hobby into a career. So all's well that ends well. By the way, I am a professor at the physics department at East Stroudsburg, which is about a half an hour over the river that way. And anybody who's looking into going into the STEM field, please check out our university. We do very well in the sciences, especially in physics. We have a very small department, and you get a lot of personalized attention. So at any rate, so enough plugs. We also have a planetarium, but I'll talk about that at the end. Okay, so the idea for this talk came to me probably a little bit, actually it was almost exactly 10 years ago. Well, not the idea, but one of the events that made me think of this talk. And that was, I think it was September, probably actually last week of August of 2011. It was after my first 2 days of classes, and I was riding my bike to get exercise because, I was getting older. I wanted to make sure I stayed in shape. And I was a little too aggressive coming down this hill going into the uphill. I figure if I pedal real hard, I won't have to pedal so hard going up the hill. Well, my foot slipped off the pedal. And you know how when something bad is going to happen to you, it's like in slow motion, and you're like, oh, I'm going to fall. I'm at the point of no return. And I went down like a ton of middle-aged bricks. And I thought, I was scraped up, my side hurt. But, I dusted myself off. I had to walk the bicycle back because it had a bent tire. And I foolishly drove to work. And I ended up in the emergency room that day because I had broken ribs. So at any rate, I was out of work for about a week and a half, and I was cursing gravity because, if gravity weren't so strong, I wouldn't have gone down so hard, and I wouldn't have broken the ribs. And the main thing about broken ribs is there's not much you can do about it. You just kind of sit there. Can I put it in a cast? No. You just have to kind of deal with the pain and hope it heals. And by the way, don't laugh. And so I couldn't even watch a funny movie. So that was a real real bummer. But okay, so then the next year, the Curiosity lander landed on Mars, and I was just kind of thinking about how cold it gets on Mars. And you know how like on a cold night here on Earth, we sometimes start a campfire. You know, that's one way we stay warm. You can't do that on Mars, right? There's no wood to start the fire. There's no oxygen to make it burn. How do you stay warm on Mars? There's no coal under the ground. You can't get anything out. And so I thought, you know, where's all that energy we use come from? And it came to me, it was like, oh, it's almost all solar energy. It's almost all, oh, I gave it away. It's almost all from the stars. Actually, it is almost all solar energy. But what isn't solar energy is from the stars, if you trace it back far enough. Okay, so that's going to be my talk tonight, and I am going to ask some questions, and I would like the kids in the audience, the young people, to try to answer the questions first. But if I don't get an answer within, say, 8 to 10 seconds, the adults are allowed to kind of jump in. Okay. I love giving this presentation when I have middle schoolers come to the planetarium because it involves other forms of science that they have learned. So energy. Without stars, especially one particular star, what star is that? The sun, we would have no energy. And without gravity, we would have no stars. So it would be a very boring universe. We couldn't be here if it weren't for gravity making the stars that make the raw materials that make up the energy that let us be here to ask questions about stars. Okay. All right, so when we usually think about solar energy, we think of this, right? We think of solar panels. These are becoming very, very common. It's wonderful to see because it's extremely clean. The sun comes out every day. Sometimes it's more intense, sometimes it's less intense, but it's always there, and it's always pouring lots and lots of energy onto the Earth. Okay, so that's solar energy. That's not surprising. Okay, it directly takes the solar energy, turns it into electricity, and it goes into your house to power your home computers and DVDs. Does anybody use DVDs anymore? It powers your house and your lights and everything. Okay. What about this? I think one of these is the Hoover Dam. I'm not sure which one. But this is several hydroelectric dams. Okay. I put to you that this is also solar energy. I know we call it hydroelectric energy, but it's really solar energy. Anybody want to try to tell me why? Okay, energy is conserved. So how can we trace back the energy that we're getting here from the flowing water? How can we trace that back to our particular star? Well, hydrogen's in the water, but yes, we have an answer. Basically, you have to have water uphill. It has to be flowing downhill. So you might say, oh, wait, it's gravitational energy. Well, yeah, it sort of is, because you have water flowing downhill. If the water didn't flow downhill, it wouldn't go down the, well, that's right, I got a point with my arrow here. It wouldn't be able to go down through the penstock, as it's called, and turn the turbine and then go downstream. Okay, basically, a hydroelectric dam is nothing more than a very high-tech water wheel. You've all seen these water wheels from a couple centuries ago, right? They were running grist mills or sawmills. The stream would run, a big, nice-looking wheel would turn, and inside you would have it crushing grain or making a saw wood. All right. But basically, this does exactly the same thing, except it's really high-tech, and it turns big magnets that generate electricity, and then electricity goes down the power lines toward your house. Okay. Now, so, am I getting enough volume on this? Okay. Okay. So how does the water get up the hill? Do we have an infinite amount of water up the hill? No, it's the solar energy that gets the water up the hill. It's the good old water cycle that you probably learned in, I don't know, early middle school, if not elementary school. Okay? No solar energy, no water cycle, no hydroelectric power. Because what happens in the water cycle? Let's review here, class. Okay? We got the sun, which the solar energy is absorbed by the water. And then we get three enations here. We got evaporation, right? And then when the water evaporates, the second enation is, no, you're skipping a step. What is it? Condensation, okay? And when it's condensed enough and the droplets get big enough, then we have precipitation. And then there's a fourth one, the running down the hill enation. I just made that one up and it's never caught on. So, but at any rate, it's the water cycle. So really, we wouldn't have hydroelectric power if it weren't for the solar energy. Okay. How about this? Windmills. These are also becoming very, very heavily used, especially in Europe. Is this solar energy? Well, why do we have wind? Does the sun have anything to do with there being wind? Does the sun have anything to do with weather? Oh yeah, it's complicated. I understand. I don't expect you to understand the details as much as the water cycle. But basically, the fact that different parts of our planet get heated different amounts by the sun means that there's going to be different amounts of air pressure, different temperatures, there's going to be trade winds, there's going to be westerlies, and there's going to be storms that form, and all of this creates wind. Without solar energy, there wouldn't be any wind. Okay, so really, when you're harnessing the power of the wind, it's really can be traced back to the sun. Okay. All right, how is this? I sort of gave a hint about this when I was talking about starting a campfire on Mars. How is this solar energy? I don't see the sun there. Was it?
I think I heard the answer out there.
Oh, okay. You went right to the root of it. Exactly. We have two things here. I'm going to back up for just a minute before we get to that word that you just said. We've got fuel, and we've got oxygen, right? What's responsible for that kind of fuel, wood, and oxygen? Photosynthesis. If it weren't for photosynthesis, we wouldn't have the wood to burn. And here's the really important part. We wouldn't have the oxygen that makes it burn and the oxygen that we rely on to live. Okay? So it's solar power that makes the wood that you burn, that releases the energy because of the trees, okay, and the plants. So it's photosynthesis. And okay, this will be on the midterm. This is simple photosynthesis. You've got carbon dioxide. Again, I keep forgetting not to point with my finger. Carbon dioxide plus water vapor, plus the energy of the sun gives you simple sugars plus oxygen, O2. Without photosynthesis, without the plants, we would not have an atmosphere with 20%, 21% oxygen. Okay? In fact, I predict that the first good evidence we will find of extraterrestrial life, if it's out there, is when we find the signature of oxygen in the atmosphere of a extrasolar planet. Okay, and we're not too far from being able to and when I say we, I mean astronomers and big observatories out there. We're not too far from having the ability to measure the atmospheres of planets that actually transit in front of their parent star. And so I wouldn't be at all surprised if that happens, because oxygen is a very gregarious element. It doesn't like to stay alone. It doesn't like to hang around in the atmosphere. It likes to, well, what does it like to do? It likes to oxidize things. It likes to make things burn, okay? It likes to make stuff rust. It oxidizes. So oxygen doesn't like to be alone. It likes to chemically combine with things. And the only reason we keep the oxygen in our atmosphere is because of photosynthesis. Okay? What about fossil fuels? All right. Are fossil fuels solar energy? No, pretty much everything I've said so far is, right? So, hate to say no. How are fossil fuels solar energy? I'll give you a hint. It's very closely tied to what we just did in the previous example. What's so fossil about fossil fuels? Was it?
Marine life.
Well, marine life, living things. It's basically organic matter that has decayed and been trapped underground for millions and millions of years. What did that living matter depend on? Solar energy. Okay? Solar energy was necessary to make the marine life, as you said, the fish, the turtles, the mollusks, okay, that die and accumulate on the seafloor. Once there were plants on land, once that happened, they died also, and they ended up getting buried underground, and they got transformed into oil, petroleum, gas, and various other things, coal. So basically, when you're burning fossil fuels, you're releasing the energy of sunlight that fell on the earth millions and millions and millions of years ago. Okay? Unfortunately, you're also releasing carbon dioxide that was safely trapped in the earth's crust for millions and millions and millions of years, back when the sun wasn't quite as bright, and now it's causing a bit of a problem, okay, because the earth needed a little more greenhouse effect back then. It doesn't need it now because the sun is brighter. The sun actually has brightened in a few 100 million years. So this is ancient photosynthesis and the food cycle. How about this? Running, jumping, my favorite sport, football. I'm so happy it's football season again. Okay. How is this solar energy? How is it that you are using solar energy to walk from your car to your seat here this evening? The food you eat, exactly. You guys are all solar powered because you had to eat food, okay? And the food that you break down, if you trace it back far enough, if you're a vegetarian or a vegan, you trace it back immediately to photosynthesis. If you're a mostly carnivore like me, you trace it back to the animals who ate the food and who ate the plants. And again, it all goes back to solar energy. So here we have a lovely dish of various types of food. We got cheese, we have vegetables, we have eggs, we have a big ugly fish. Okay, but again, the food pyramid is basically you've got the carnivores, and somewhere in there in the middle you got us, which are the omnivores. Okay. Well, photosynthesis, again, photosynthesis, carbon dioxide, H2O, and energy makes simple sugars and oxygen. Aerobic respiration, basically, when you breathe in, you get energy out. And that's because you also get carbon dioxide out. It's basically reverse photosynthesis. So when you're digesting your food and you're using those simple sugars you've digested, and you're breathing out that carbon dioxide and producing the energy you need to walk and to jump, do whatever, that's energy that you got from the food that came from the sun, from the photosynthesis that you're now reversing. When I finally looked into this, I'm like, wow, that is really kind of awesome, isn't it? It's like, it's solar energy if you trace it back far enough. So even we are solar powered. Okay. All right, now we come to nuclear power plants, or at least I think these are nuclear power plants. They have those cooling towers that all nuclear power plants have. I didn't really check because I found out that other power plants use cooling towers too, but let's pretend that they're both nuclear power plants. Okay, is this solar energy? I know you all want to say yes because I've been baiting you into saying yes for every single source of energy so far. Now, this one isn't. This one does not come from the sun. But it is star power. It is powered by the stars because the fuel that you get, that you need for nuclear fission, which is the type of nuclear energy we use in nuclear power plants, does not come from the sun. It comes from other stars. Okay? You need uranium, which is the heaviest naturally occurring element that we can find on Earth. Okay? The universe started out as nothing but hydrogen and helium. Okay? You can't get a lot of interesting things out of hydrogen and helium. First of all, you have a very small periodic table. You only have 2 squares, and you wouldn't have anything to write those 2 squares on. Okay? Or you wouldn't have anybody to write it either, because it would all be hydrogen and helium. Okay? And hydrogen and helium is really boring. There's not much of a universe that's interesting with hydrogen and helium. But the hydrogen and helium comes together because of gravity to make stars. And it's the stars that are the manufacturing plants, especially the really, really heavy stars, the real show-off stars of our galaxy and other galaxies, that eventually form these heavy elements. And also, if they formed those heavy elements and it stayed stuck inside the star after it died, that wouldn't do us any good. There wouldn't be any solid planets. There wouldn't be anything solid for me to stamp my feet on right now. That stuff has to get out to be useful to you and me, to make a nice solid planet like the Earth. But luckily that happens. Okay? But let's go back to uranium. So basically, uranium in a fission plant, fission means to break apart, like a fissure in a rock is a crack in a rock. So when you slam an atom of uranium with a neutron, it splits apart, a bunch of neutrons come flying out, which makes a few things radioactive, which is not very nice. And also a couple of nuclei, waste nuclei, come out. Unfortunately, they got a little too many neutrons in them too, and they're kind of dangerous because they're radioactive too. But, we'll bury them somewhere. Okay. There's a lot of problems with nuclear fission. It's not the ideal case, but it doesn't give off any greenhouse gases, so that's the plus side. But it's kind of dangerous, and nobody wants the waste buried in their backyard. Okay. And basically what we do with the nuclear fission is we boil water. You might think, wow, that's a kind of a high-tech way to boil water. Yeah, it is, but it's also a very efficient way to boil water. So what we have is a very high-tech glorified steam engine that turns the turbines, just like the hydroelectric dam turn the turbines, and then makes power that goes to your house to power, so you can charge up your cell phones and your laptop computers. Okay? And so you can watch YouTube, because everybody's got to do that. So all the uranium on Earth and in the universe is created in supernova explosions. Supernova explosions are what happen after really, really massive stars. We're talking stars that are at least more than 9 or 10 times the mass of our sun, probably more like 20 times the mass of our sun. When they reach the end of their life, basically their entire life is a struggle against gravity, because gravity is what turns the gases of what we call the interstellar medium, which is just gases in between the stars. It sounds like somebody who can read your mind, the interstellar medium, but it's not. The gases between the stars get pulled together. They get clumpy enough so that gravity pulls them together. Gravity is pulling things together. It's a very, again, very gregarious force. It tries to pull stuff together. And it does. It makes stars. And stars are hot because of the gravity that heats it up when they get smaller and smaller and smaller. But eventually there becomes kind of an equilibrium, a balancing act, where the force of gravity trying to make the star shrivel up, kind of like a balloon. If you take the knot out of the balloon, it shrivels up, right? But it's the gas pressure on the inside that's being created by the heat, by the nuclear fusion, that keeps the star from collapsing. So our sun is going to come up tomorrow morning. It's going to be the same size in the sky. We can be pretty confident of that for at least the next 5 billion years. Okay? But eventually, stars run out of gas. They don't run out of gas, they run out of fuel. Okay, they run out of useful fuel. Now stars are very clever. Well, they're not really clever. They're actually fairly stupid. But nuclear physics is very clever. The physics of stars is very clever because stars naturally start to shrink and heat up, and they start to burn their garbage. Okay, our sun is going to become too contaminated with helium, and eventually it's going to be pulled in by its own gravity, but it's never going to get hot enough to burn helium. But really massive stars do burn helium. They burn their garbage, and then they make more garbage. They make carbon. But if they're really massive, they get hot enough even to burn carbon in nuclear fusion. And when they run out of that, they get I'm trying to figure out what's next. Oxygen and silicon, all the way up to iron. Okay, actually I'm getting a little bit ahead of myself, or at least I'm getting ahead of these slides. Okay, so if it weren't for stars, because it's when stars explode after they finally get to that iron stage, when they just go out with a bang, they go kablammy. Okay, that's when all the elements on your periodic table, all the elements that are heavier than iron, like silver and gold and lead and uranium, okay, and lots of other ones that I can't pronounce. Okay, I haven't had chemistry since high school. So all of those elements were formed inside the supernova explosion. In fact, in a very short time, in something like a half a minute during the supernova explosion, all those elements are found. Okay, and in fact, an astonishing factoid I remember from one of the documentaries, that was a BBC documentary by Brian Cox, who I'm sure you've seen on TV. He's an awesome astronomer, an awesome explainer. He says basically, in a galaxy like our Milky Way, you're going to get about 2 supernovas per century, on average. And during those supernovas, for maybe a half a minute, you get heavy elements being created. So that means that every century, the conditions for making stuff like gold and silver and uranium and lead is present in an entire galaxy for about a minute out of each century. And yet, that's what our Earth is made of. The stuff that's, well, not all of it, but a lot of it is the stuff that's created inside supernovas. Okay? But that's also why gold, by the way, is so rare. It's because it's made in these supernova explosions and not by regular nucleosynthesis, which is what we call making heavy elements out of lighter elements inside stars. Okay? So if it weren't for gravity, we wouldn't have stars. Gravity forms stars out of these clouds of gas and dust, the interstellar medium. Gravity squeezes the star to make its core hot. The hot core makes energy by nuclear fusion. Okay, nuclear fusion is a little different than nuclear fission. The nuclear fusion that our sun makes is where 4 hydrogens, 4 protons, which are hydrogen nuclei, come together in all these complicated steps. It has to be super hot for that to happen because hydrogens have positive electric charge. So it's like trying to slam together 2 north poles of a magnet. They have this automatic collision avoidance system because they have the same electric charge. They don't like to, it's like bumper cars that don't allow themselves to bump. So what do you have to do? You got to slam them together even faster to make them bump. But once they bump, it's like they have super glue on them because when they touch, they lock together because of something called the strong nuclear force. And so if you get it hot enough, you can turn these hydrogens into a helium. Now, funny thing is, helium is a heavier element than hydrogen, but it takes 4 hydrogens to make 1 helium nucleus. And if you had a little teeny tiny scale, like a little teeny tiny balance like you have in chemistry class, and you put 4 hydrogens on one side and 1 helium on the other side, the 4 hydrogens would be ever so slightly heavier And that's because the helium has lost, the particles that make up the helium have lost a little bit of mass in the process of making helium. And that's where the energy comes from. Because it turns out that mass and energy are two forms of the same thing. Any of you Einsteins out there want to tell me what equation tells us that? That's a hint. E equals mc squared, exactly. Energy is mass times the speed of light squared. Basically, energy and matter are two forms of the same thing. They are not easily interchangeable, and that's actually a good thing, okay? Because it would be a very dangerous world if they were easily interchangeable. But a little bit of energy, if you lose a tiny bit of energy, like 0.7%, like in this process, if you lose a little bit of energy, you have to multiply it by the speed of light twice. You got to multiply twice. You got to multiply it squared to get the amount of energy you get out. Okay. What I like to tell my classes is, if I took a paper clip, just a normal sized paper clip, if I could somehow turn the mass of that paper clip into energy, roughly how much energy do you think that would be? Any guesses? Firecracker? Stick of dynamite? A lot more than that. You'd be able to launch the space shuttle into orbit with the energy from a paperclip. Okay, so there's a reason they told you in chemistry class that mass is conserved. It's actually a lie. It's not really conserved, but in chemistry, in chemical reactions, only about 1/billionth of the mass is lost and turned into energy. They're not very efficient reactions. Okay, this is why the sun can burn for billions of years. This is why stars can burn for billions of years, whereas if it was chemical energy that was making them shine, they would burn out in the sun would burn out in about 10 million years. That sounds like a long time to you and me, but that doesn't even get us back 1/6 of the way to the dinosaurs. Okay, so the sun burns about 1,000 times longer because nuclear energy is about 1,000 times more efficient. You get 1,000 times more bang for the buck for the fuel in nuclear energy. Okay, but the cool thing is you also get out heavier elements, and heavier elements is what we need to make you and me and the green grass and the trees and the telescopes and all the cool stuff around us. Okay, so when the nuclear fuel runs out, as I said before, gravity wins, the star's core begins to collapse, and then boom. Again, this will not happen to our sun. Our sun is a small star, okay? But our sun will become a red giant, and don't worry, this is going to happen in 5 billion years. By the way, I remember saying that once, and no, actually I didn't say it, but somebody who was visiting our observatory over at East Stroudsburg was asking me, he said, so is our sun going to be turning into a red giant in 5 million years or 5 billion years? And I said, 5 billion years. He said, oh, thank goodness. Like, were you going to lose sleep at night over this? 5 billion? But anyway, it is good that it's 5 billion, not 5 million. Our sun will eventually blow off its outer layers into space to form this beautiful smoke bubble ring thing called a planetary nebula, which is one of the things I studied when I was in grad school. And by the way, it has nothing to do with planets. Astronomers are really weird this way. An astronomer a few hundred years ago, when they first saw planetary these little ring-like or disc-like things through a telescope, he thought that they looked sort of like a distant planet, so he called it a planetary nebula. Okay, it's a nice little description, but for 4 to 6 years I had to keep answering when people would ask me what I was doing for my dissertation. I would explain, and at the end they say, well, where's the planets come in? I said, well, there's nothing to do with planets. I mean, we know there might be planets in there, but that's not why it's called a planetary nebula. Anyway, our sun will become a white dwarf. In other words, it will shrink to the size of the Earth. And when it shrinks to the size of the Earth, pretty much let's say if you have about a sugar cube of material, let's say, everybody knows what a sugar cube looks like, right? It's about this small. I put them in my tea all the time. That would weigh about as much as a fully loaded dump truck. Okay, so imagine putting a fully loaded dump truck into a trash compactor or crusher and crushing it down to the size of a sugar cube. That's what a white dwarf is. Okay. A really massive star blows up as a supernova, and it leaves behind one of two things. It leaves behind either a neutron star or a black hole. Okay, the mysterious black hole. A neutron star makes a white dwarf look like no big deal. If you took a sugar cube of neutron star, I certainly wouldn't be able to hold it. I mean, I wouldn't be able to hold the white dwarf star, sugar cube either. But a neutron star sugar cube would weigh as much as a large alpine mountain, maybe even Mount Everest. Okay, so if you crushed Mount Everest to the size of a sugar cube, that's how dense neutron star material is. But eventually, if you get a neutron star that's about 3 times as heavy as our sun, even the packed together neutrons aren't strong enough to dissuade gravity from crushing it even smaller, and you end up with a black hole. And I'm not going to go into a black hole because that'll be another hour. Okay, but black holes are basically neutron stars that are so small that they disappear from sight because the speed of light isn't fast enough to let light get out. So basically, next time you trip and fall down, don't curse gravity. Because if it weren't for gravity, there wouldn't be stars. And if it weren't for stars, there wouldn't be energy, and there wouldn't be the molecules of atoms that make up you and me, and the food you ate, and the stuff you get your energy from. So gravity is good. Gravity is a good thing. And so are stars. And that's one of the reasons I love them so much. And I'm so glad it's a nice clear night tonight. So that is pretty much the end. Oh, wow. Okay. Took longer than I expected. I think I embellished a little more than I do with my middle schoolers because they don't have as much time when they get to the planetarium. But so I guess this is where we open it up for questions.
All right. Hello? Hello? Does this work? Is it working? Okay. I know sometimes it doesn't like working after a while, and yay, technology gremlins. They never strike the same way twice. Anyhow, thank you very much for the presentation.
My pleasure. Thank you for coming.
How we do this is, like I said at the beginning, I've been monitoring chat. So now we will open this up to a question and answer session. So what's going to happen is if there's a question online, I do read it out from my mobile device. But I'm sure you guys also have questions. I just ask that when you have a question, you raise your hand and kind of wave it around because I have trouble seeing at night. Second, I'm going to come over there with the microphone so you can speak into the microphone. Because chances are, if you have a question here, our online audience probably has a similar or the same question. Or, like last week's presentation, sometimes it starts a really interesting discussion and questions build off that way. So, with that note, I'm going to start us off with an online question, as I have to scroll up a little bit. Someone asks, so we have oxygen that likes to burn things, and antioxidants are a very important part of our diet. Does that mean since the moment we are born, we are slowly being set on fire or oxidized very, very slowly?
Metabolism is not my field of study. So I know that, basically, yeah, oxygen kind of wears away at us from what I've heard, but I really probably don't feel qualified to say that. I do feel qualified to say that aerobic respiration, I like to tell, one thing I forgot to say is, when we did the running and jumping and tackling and everything, there's a fire inside you. It's like you have a fire inside you. It's just a very low temperature fire. It's 98.6 Fahrenheit fire.
Oh, you mean that wasn't the indigestion?
No, that wasn't the indigestion. Well, it might have been actually, but we have a 37 degrees Celsius fire inside us. it's a little more complicated than just combustion. There's like ATP and stuff that goes on, and it's a more complex chemical reaction, but it is like a fire. And but as far as antioxidants go, I don't want to go there, actually. I'm not qualified enough to do that.
All right. Do we have a question from our audience here? And like I said, you're going to have to kind of wave your hand up because I have trouble in the dark. Anyone? Oh, there we go.
There's a concept, I don't know if it's science fiction, called Dyson spheres, where people create structures around a sun or star to capture all the energy.
Okay.
Do you think that this is feasible in the distant future with the advanced civilization? Do you think that might be possible?
I suppose in the future, anything, if you go far enough into the future, and if we manage to survive long enough, or some other civilization has managed to survive enough to do it, that it would be possible. Yeah, I mean, really, when you put solar panels in a desert, what you're doing is you're making one little tiny patch of a Dyson sphere. What the Dyson sphere does is it collects all of the energy of the star. Now, the planets outside that sphere might not like that very much. So that might be a bit of a problem. And in fact, if the Earth were on the outside and we were collecting all we don't need that much energy. That's way more energy than we need. But yeah, I mean, theoretically that's possible. In fact, I use that concept a lot to try to have people understand why stars are dimmer with distance. Because if you surrounded a star with a bubble, a transparent bubble, how much energy of the star goes through that bubble? Well, all of it does. Okay? But if you made a bubble that was twice as big, it turns out that the light, by the time it goes through that second bubble, has thinned out to 1/4 the intensity. And so if you go twice as far, you don't have a star that looks half as bright. It looks 1/4, 1/4 as bright. And if you go 3 times as far, then it spreads out over 9 times the area of that first bubble, and you have a star that looks 1/9 as bright. So here's kind of a cool thing. If you went to Jupiter, Jupiter is about 5 times as far as we are from the sun, and it's right over there. Okay, it's pretty bright. But the sunlight falling on Jupiter, the intensity of the sunlight falling on Jupiter, because it's 5 times as far as we are, is 5 squared, or 25 times dimmer than it is on Earth. Okay, so the intensity of light on Jupiter is like 1/25 of the sunlight on Earth. And in fact, when the Voyager spacecraft flew past Neptune back in 1989, they had trouble imaging the planet because the cameras were built in the early 1970s, so they weren't very light sensitive. But the intensity of sunlight at Neptune, which is 30 times as far from the sun, is 30 times 30, or 900 times dimmer. So it's like lit up by candlelight practically. I'm exaggerating a little bit, but it's not very bright at all out there. And they had to actually program the spacecraft because the people at JPL are geniuses. They actually programmed the spacecraft to follow the planet to compensate for their trajectory so that it would expose long enough to get a clear picture. And so anyway, I've embellished on your question, but yeah, the Dyson sphere is a very useful concept, because when we collect sunlight, what we're doing is we're collecting an area of rays of light that are falling on us, and the more we collect, the more energy we'll get. So, great question.
All right. It looks like I had a couple of smart Alex in chat.
Oh, great.
I couldn't let this comment pass by.
I didn't tell my students about this.
I'm You should have. It looks like this is in response to when you were talking about how stars take hydrogen and helium and compress them into other elements.
Right.
They said, oh, look, you took hydrogen and helium and compressed them until they got anxiety, meaning they formed us.
Okay.
Yeah, if anyone's online and recognize memes, that's a very old meme. And it tickled my funny bone just a little.
It's cute.
All right. So on to the actual question. What's your favorite form of solar-derived power?
Favorite form?
Yeah, you covered
well,
when
when I'm sitting around a campfire, I like that the best. when I'm in my nice toasty house, I prefer the propane that is burning in the boiler. I guess whatever's keeping me warm. I really don't have a favorite. I think as far as obviously environmental concerns are, wind power is excellent. You know, solar panels are excellent. Even burning firewood is not so bad if you replant the trees. Okay, so as long as you don't have a net loss of wood, you're still okay, because there's a difference. This is getting a little off topic, but there's a difference between burning fossil fuels and how that's bad for the environment compared to burning wood in a campfire. Wood in a campfire is combustion, and it gives off carbon dioxide and gives off, greenhouse gases, and that contributes to global warming. But the carbon dioxide in that wood was only put into that wood, or at least the carbon that's from the carbon dioxide that was put into that wood was only put into that wood a few years ago, when the sun was the same luminosity as it is now, when we had the same amount of carbon dioxide roughly as we have now. But a fossil fuel was from not a completely different Earth, but a much different Earth. An Earth that had a lot more carbon dioxide in its atmosphere, but it was okay because the sun was dimmer. And it didn't affect the environment quite as much. Also, we weren't here. So civilization wasn't here to have to deal with the consequences of the Earth getting too warm. But basically, when you're releasing that carbon dioxide from millions of years ago, there's a net gain in the atmosphere, and that's why it's a problem. So, still, only burn wood if you're going to replant it, or somebody's going to replant it for you. So.
All right. So, do we have another question from our live audience? I know someone's got to have. Someone had their cell phone. That's great.
Since the stars are so distant from each other,
yeah,
when they explode and go supernova, what's the next step on how all those new elements get to like a planet? I mean, what's the next step after the explosion?
Okay, excellent question. Yeah, that's basically the interstellar medium. Those gases circulate through the galaxy and eventually form clouds of gas that get dense enough to get clumpy enough to form new stars. But it's a long process. It's not like, a supernova happens and the gases immediately turn into new stars. It could be hundreds of millions or billions of years before that happens. But yeah, so for example, the Earth and the planets came out of the nebula that the sun was formed from, and we were basically the leftover stuff that condensed into planets. But the materials that make up you and me and the atoms inside your body and everybody else's is not from one single star that blew up. It's from the combined gases that circulated through the galaxy more than 5 billion years ago before our solar system formed that turned into eventually our planets. So yeah, it just kind of, what goes around comes around, I guess. So yeah, the interstellar medium is just made of the gas of exploded stars, and it's in the disk of our galaxy. It's been swirling around, and sometimes just by chance, other times because of gravitational waves through the galaxy, not gravitational waves, but density waves like the spiral arms of our galaxy. It can get clumpy enough to turn into new stars, and we see that as emission nebula. So. Yeah.
Right. Like I said, online chat has been a little fresh today. The next comment is referring to black hole. It's a black hole. Instead of an hour, wouldn't it be a topic you kind of fall into and never get out of?
Yeah, you rarely climb out of one of those. Yeah.
Like I said, online chat has the jokes tonight. So, on a topic of an actual question, we've been getting all of this energy from the sun. Where does it go when we expend it?
I'm sorry, say again?
So we've talked about how we get all this energy from the sun or stars.
Oh, yeah. Mm-hmm.
Where does that energy go when we expend it?
Oh, mostly it goes into waste heat. It goes into waste heat, and for example, you guys are all, giving off as much energy right now as an old-fashioned 120-watt light bulb. Okay, people, you're not as bright as one because you're at a much lower temperature, but your luminosity, your amount of energy that you give off per second, is about the same as a 120-watt light bulb, and that's why crowded rooms get very warm. And it goes into the environment and it heats it up, and on a clear night like tonight, it gets actually radiated into space. So, but that's a really good that reminds me of another interesting thing, and that's because if you did make a Dyson sphere or had an unlimited amount of energy, and you used as much as you could, that wouldn't be good either, because then you would heat up the environment just from the expending the energy. You wouldn't need a greenhouse effect. You would actually, wouldn't need global warming. You'd be doing the global warming directly instead of trapping energy from the sun. So yeah. But right now, we're not even close to that. The energy we use on the everyday thing basically does get radiated back into space.
All right. Do we have another question out here? Do we have any questions from the back row? Sometimes I really hope we have questions. And honestly, I really like her technique of having her phone up so I could actually see it. If you all had questions at once, it could kind of look like we're in the rock show. Anyone? Bueller? Bueller? All right. So it looks like I'm going to put out a last call for any questions on our live stream side of things. So let's get my tongue unwrapped from around my eye teeth so I can see where I'm speaking. So I want to thank everyone for coming out tonight. I want to thank everyone who joined us on our online stream. A couple things for people who are here live in person, since I do know a couple of you kind of snuck in during the presentation. If you need to use the bathroom, like I said at the beginning, we have the porta potty with the red light on it to my right, your left. We also have the sales desk. I will be going in there to man it as soon as I end the stream. So after this, all the sheds that you saw when you were coming in here over there, each one of those does contain a telescope. And tonight we do have a couple of those observatories open. Most of them, with the COVID restrictions and the fact that the constant sanitation would destroy the optics in the eyepieces, we have put cameras where we would normally put our eyepieces and actually have the image you would see through the telescope projected onto a screen onto the side of the observatories for you. There may also be a couple telescopes set up on the lawn. Do be mindful if they do allow you to look through the eyepiece. It is not actually one of the UACNJ owned telescopes. And please, if you are not feeling well or what have you, be mindful of other people and let's not look through the telescope just because, safety first. That being said, any lights you need to see to walk around, please keep them pointed down towards the ground because we like being able to see, and having lights in our eyes is painful. However, you can't move headlights down to the ground, but we still ask you use your headlights because we also don't like getting run over. Been there, done that, did not enjoy it, would not recommend. So, it looks like that was the only question from our online chat. I want to thank you all for joining us.
Say one more thing before I say so long?
Yep.
Yeah, one little plug I want to mention for any of you who might be traveling through the Poconos at some point on a weekend. We do have a wildlife museum and the McMunn Planetarium in our SciTech building on East Stroudsburg campus. And it's right now it's going through, our projector is 13 years old and it's somewhat low def, so it looks a little bit antiquated, but we are getting a brand new one that should be up up and running by next spring. So they're usually open on Saturdays from about 10 to 2 or 3. I can't remember exactly what. But if you're there in the middle of the afternoon, come see. It's fairly inexpensive, and but it's really a pretty impressive facility. And we'd love to let you come in and see a few star shows. Alrighty.
And now, if they wanted to go see this, could they look up that information online? And
They
what
sure
website
could.
would they
You
go
just
to?
just look at East Stroudsburg University and ask for the just put in the search line planetarium or wildlife museum, and that should be good enough.
Right. I want to thank you for a
My
great
pleasure.
talk.
Thank you
I want
guys
to
for
thank
coming.
our both in-person and online audience. Thank you for being great. And like I said, be safe out there. Have a good night.
All right.
All right. You should be able to.